to do is add 1 to that exponent and then divide by that. There's already a 1 there, so I'm going to add 1 to the 1 already there. So this is going to give me an antiderivative of 3x to the third over 3, divide by that, plus 2x, add 1, squared, then divide by the exponent, plus c. But I can simplify that a little bit, and you're going to want to do that. So that's going to give me x cubed plus x squared plus c as my final answer because the coefficients simplify. For number 2, you're just supposed to know that the integral of e to the x is e to the x, but then you add some constant c when you're done. The integral of 1 over x, again, you're supposed to know that the derivative of ln x is 1 over x, so the antiderivative of 1 over x is just ln x plus c. This one you're going to do a little house party with and bring that exponent upstairs so I can implement the backward power rule. So that's going to give me equals the integral of x to the negative fourth dx. Now I'm going to add 1 to the exponent, and that's going to give me x to the negative third. Then you divide by that exponent, negative 3. We're going to rewrite it. I should have put plus c. We're going to rewrite it, and that's going to equal negative 1 over 3x cubed plus c. Negative 1 over 3x cubed plus c. The integral of cosine, well, you're going to want to know this little trick. It's going to be the derivative of sine. The derivative of the sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is actually sine. So on the way down, these are derivatives, and on the way up, these are integrals. So I want to know what the antiderivative of cosine is. So the integral of cosine is just plain old sine x plus c. For number 6, the integral of sine is negative cosine. So that's going to give me negative cosine x plus c. The integral of secant tan. Another little trick is to use this note. Secant, secant, tan, cosecant, negative cosecant, cotan. So the derivative of secant tan, the derivative of secant is secant tan. So the antiderivative of secant tan is just secant x plus c. The derivative of secant squared. So, tangent, the derivative of tangent equals secant squared. The derivative of tangent equals secant squared. So the antiderivative of secant squared is just tangent. So this one's going to be tangent x. Now I can't immediately find the integral of this, so what I'm going to do is write them as fractional exponents. So that's going to give me x to the something over 3, and that's technically a 1 there, so that's 1/3, minus the integral of x to the, there's a hidden 1 there, I add 1 to that, that's going to give me x to the, x to the 1/2. I'm not adding yet. All I'm doing is simplifying it. So that's x to the 1/2 dx. Now I'm going to implement the backward power rule. All I have to do is add 1 to each of these exponents. This is going to give me a new integral of x to the 4/3 minus x to the 3/2. But then don't forget I have to multiply by the reciprocal of the fraction. So it's 3/4, and this is 2/3. So my final answer is going to be 3/4 x to the 4/3 minus 2/3 x to the 3/2. The antiderivative of e to the 3x is e to the 3x, but then I take the derivative of that, which is 3, and I divide by that derivative. Don't forget to add the constant c so the equal sign is legal. So this is going to be e to the 3x over 3 plus c. This here is going to be 2/3 3x minus 5 to the 3/2 minus, plus c. And I'm going to do that one by hand so you can see the whole. Let me try number 11 again from the top using the substitution instead of just using some sort of memorization process. I'm going to let u equal 3x minus 5. So the derivative of that equals just 3 dx. So my integral is going to be the square root of u du with a 1/3 out front. Now, I want to rewrite this in exponential form so I can use the reverse power rule to take the derivative of it, the antiderivative of it. So it's going to give me 1/3 integral of u to the 1/2 du. And now I add 1 to the exponent, and that gives me u to the 3/2. Then I multiply it by the reciprocal of that, which is 2/3. But don't forget, I have the 1/3 multiplied by this antiderivative. And that's going to give me 2/9 u to the 3/2. But remember this, that u equals 3x minus 5. So that's going to give me a final answer of 2/9, whatever u equals, to the 3/2 plus c. And whatever u equaled was, originally, the square root of 3x minus 5. Or in this case, just 3x minus 5. That's what I let u. Going to do a u sub, I'm going to let u equal x to the 3rd. Then when I take the derivative of that, that gives me du equals 3x squared. And then you'll notice, 3x squared dx actually. Then you'll notice I have an x squared dx, an x squared and a dx. I also have a 3 out front. So everything basically substitutes with the u substitution. And that's going to give me e to whatever I let x to the 3rd equal, u. Now I'm in what we call the u world. And the antiderivative of e to the u du is going to be e to the u. I'm not going to put my plus c until I back substitute in the x cubed. So this is going to give me e to the x cubed plus c. Over here, I'm going to let u equal this complicated expression inside the parentheses. So I'm going to let u equal 2 plus x to the fourth. Take the derivative. That gives me du equals, the derivative of 2 is 0, derivative of x to the fourth is 4x cubed du. Now I look to see if anything cancels or lines up. It's actually dx. And notice this whole thing cancels out with 4x cubed dx. That's why that had to be du, and that has to be dx. And that's just going to give me a new integral in the u world of this quantity u. Du now. I get the du from that. Antiderivative of u du is going to give me u to the second over 2. Now I'm going to back substitute. Plus x to the fourth. So this is going to give me 2 plus x to the fourth all over 2 plus c. For this one, I'm going to let my u equal x cubed plus 1. And one of the reasons I let it equal x cubed plus 1 because I notice instantly that when I take the derivative of x cubed, it's going to give me an x squared. So du equals 3 x squared dx. I notice that an x squared dx simplifies. But I'm stuck with this 3 this time, so I have to divide both sides by 3. And that's going to give me in the u world an integral of 1/3 of something du. And that something is going to be a square root. The square root of whatever I let the inside equal, u. And now I have to go ahead and take the antiderivative of this. I'm going to rewrite that as 1/3 u to the 1/2 du, so I can deal with the exponents. I have to add 1 to that exponent, and that's going to give me 1/3 u to the 3/2. Then I multiply it by the reciprocal of that. Notice I brought the 1/3 with me, so the reciprocal of 3/2 is 2/3. This is going to give me another u, which is going to be 2/9 u to the 3/2. Now I'm ready to back substitute in my x cubed plus 1 to write the answer down. So it's going to be 2/9 parentheses x cubed plus 1, because I'm going back to the x world from the u world. There's my u to the 3/2 plus c. Okay, graphing. I have to graph x squared and x to the fifth. Well, x squared, we know the array of points is 1, 3, 5, 7, so it's going to go like that. I'm just going to freehand it. And x to the fifth, we should have learned, is going to be like this, because it's an odd function. And I want to know where those two intersect, and I want to find the area of the shaded region enclosed. Let's see, to find out where they intersect, I can see instantly it's at the coordinate 0, 0. But I'm going to do it algebraically here. I'm going to set x squared equal to x to the fifth. So that means I'm going to subtract x squared from both sides. That's going to give me x to the fifth minus x squared equals 0. I'm going to factor out x squared. That gives me x squared times x cubed minus 1 equals 0. I set x squared equal to 0, and I get 0. That's how I got that one. I set x cubed minus 1 equal to 0. I add 1 to both sides. That gives me x cubed equals 1. When I cube root both sides, notice I get x equals 1. So they intersect at x equals 0 and x equals 1. If I throw that back in, it's actually going to be the coordinate 1, 1. Now I have my limits of integration from 0 to 1. The rest of the integral setup is going to be the top graph minus the bottom graph. And the top graph is the x squared. The bottom graph is the x to the fifth. I can either take the antiderivative by hand or use the technology. I'm going to do it by hand. So I add 1 to that, so that's going to give me x to the third divided by 3 minus x to the sixth divided by 6, leaving its notation from 0 to 1. Now I'm going to set up my template, something squared, or I'm sorry, something cubed, over 3 minus something to the sixth over 6 minus a big quantity now because I have to distribute that negative. The same template, something cubed, over 3 minus something to the sixth over 6. I plug in the 1 up front. And this is nice. I plug the 0 in the back, and this all goes to 0. So this is going to be 1/3 minus 1/6. To find what those are without a calculator, I'm going to use this method called the algebra 2 method. The minus sign goes on top. 3 times 6 is 18. 6 times 1 is 6. 3 times 1 is 3. So that's going to give me 3 over 18, which should give me an area of 1/6. No plus c. My next area is going to be x squared and x to the fourth. So x squared is actually a little bit narrower than x to the fourth. X to the fourth is going to sort of belly out and then come down. It's actually more like the Miami U University shape. They intersect at 0, 0. And I think you'll start to notice that these graphs also intersect at 1, 1. I can show you the algebra by setting them equal to one another. X to the fourth equals x squared. Bring over the x squared. That gives me x to the fourth minus x squared equals 0. Factor out x squared. That gives me x squared times x squared minus 1 equals 0. That is going to be 0 when I let x squared equal 0. And that's going to give me two answers. X squared equals 1. X equals plus or minus 1. And notice they also intersect over here at negative 1, 1. I'm going to use different limits of integration. I'm going to use it from 0 to 1. But because it's symmetrical, and I have this area and this area, I'm going to put a 2 out in front of my integral. And that makes this legal. You could have done from negative 1 to 1, especially if you're using a calculator. It'll generate the answer from negative 1 to 1 just as quickly as it will from 0 to 1 times 2. It doesn't matter. The top graph, when the area of shading, is going to be x squared minus the bottom graph, which is x to the 4th. I'm going to do it by hand. It's not a difficult integral. So it's going to be the out front, the 2, times x cubed over 3 minus x to the 5th over 5. Leibniz notation from 0 to 1. I'm going to set up my big brackets because I have a 2 out in front. That's going to be a template of something cubed over 3 minus something to the 5th over 5 minus, I'm going to use parenthesis inside a bracket. Another template, x cubed over 3 minus something to the 5th over 5. Close that because I have to distribute the negative across. Now I'm going to plug in my limits of integration, 0 in the back and 1 up front, so I put the 1 in up front. And the 0 in the back. And notice this is nice, this all goes to 0. So this is going to actually give me 2 times 1/3 minus 1/5. And I'm going to use my algebra 2 method to add those fractions. That's going to be 15 on the bottom, 5, 3, so that's going to give me 2/15. But don't forget I have to multiply, I have to multiply that by 2. So that's going to give me 2 times 2 over 15, and my final answer should be 4 over 15.